welcome back. Today we will start Lecture 5-3 and continue a discussion of frequency response design, phase, lag, and lead compensator design. The objectives are to describe the benefits of using lead and lag compensation for control system design, to apply lag and lead compensation to improve the characteristics of a control system such as steady state accuracy, phase, and gain margin, and to describe the benefits of a lag lead compensator for control system design, and to design a lag lead compensator to improve characteristics such as steady state accuracy, phase, and gain margin. A lag lead compensator is used to improve the transient and steady state response of a control system. The design technique involves adjusting the gain K to satisfy the steady state error requirements, and then the next step is to use the lag compensator to maintain the steady state characteristics. Lastly, use the lead compensator to meet the transient characteristics such as phase and gain margin, percent overshoot, settling time, and peak time. Figure 1 below shows the Bode diagram of the lag lead compensator, and it also illustrates a band reject filter. So here on our figure, we call this a band reject filter because right here at this certain amount of frequencies, there's actually a dip in the magnitude. But the other interesting thing to note is that it's a lag lead filter because here we have a dip in the phase angle, which represents the lag, and then here we have a spike in the phase angle, which represents the lead. GC of S is equal to G lag times G lead, which is S plus Z lag over S plus P lag, times S plus Z lead over S plus P lead. We can also express this as S plus 1 over T lag over S plus 1 over beta T lag, times S plus 1 over T lead over S plus 1 over alpha T lead, where alpha is between 0 and 1, and beta is greater than 1. It's important to notice here that P lag is less than Z lag, and conversely, P lead is greater than Z lead. Some of the relevant formulas that we will use in this design process we have used before, but here's a summary. Sine phi m is equal to 1 minus alpha over 1 plus alpha. That's the phase angle where the magnitude is maximum. Omega m is that frequency, and it's 1 over the square root of alpha t. The natural frequency is 4 over the settling time times the damping ratio zeta. The natural frequency can also be written as pi over the time to peak divided by the square root of 1 minus zeta squared. And the frequency bandwidth can be found by using the natural frequency, omega n, times the square root of the quantity 1 minus 2 zeta squared plus the square root of 4 zeta to the fourth minus 4 zeta squared plus 2. And finally, the phase margin, which is equal to the arctangent of 2 zeta over the square root of negative 2 zeta squared plus the square root of 1 plus 4 zeta to the fourth power. Steps to design a lag lead compensator. Step 1, determine the gain K to satisfy the steady state error requirement. Step 2, plot the Bode diagram of the open loop transfer function with the gain K found in step 1. Then for the lag compensator, determine the uncompensated phase margin from the Bode diagram. If the required phase margin is given, go on to step 4. If the required phase margin is not given, then calculate the damping ratio from the percent overshoot requirement and calculate the required phase margin from the damping ratio zeta. If the time to peak or settling time are given, calculate the natural frequency omega n from the time to peak or the settling time. See the table above for the formulas to do this. Next, calculate the required bandwidth from the natural frequency. See the table to do this as well. Or let the new phase margin frequency omega sub pm equal 0.8 times the frequency bandwidth. If the time to peak and settling time are not given, let the new phase margin frequency omega sub pm equal the uncompensated gain crossover frequency omega gc. Step 5, determine the uncompensated phase theta at the phase margin frequency. Step 6, calculate the required phase angle, phi equal negative 180 plus theta plus the phase margin plus 5 degrees, a correction factor that we put in because the magnitude does drop slightly when we do this. Step 7, determine the gain beta equal to 1 plus sine phi over 1 minus sine phi. Step 8, set the lag compensator 0, Z lag equal to 0.1 omega p sub m. And 9, set the lag compensator pole P lag equal to Z lag over beta. Finally, Finally, to design the lead compensator, let alpha equal 1 over beta. Set the lead compensator 0, Z lead equal to omega p sub m times the square root of alpha. And set the lead compensator pole P lead equal to Z lead over alpha.